It's a great honor to give this lecture in front of the Dutch biophysics community, and I thank the organizers for giving me the opportunity to do so. I'm going to talk about very simple membranes, also seen here, which we call artificial cells. To introduce them, let's start with a cartoon of the cell. If you zoom in into the plasma membrane, you're going to find the zoo of molecules. If you throw out all the proteins, you're going to end up with a simplified model system, a lipid bilayer. If you do the same minimization to the cell, you're going to end up with what we call artificial cells in this case, and these are giant and lamellar vesicles. They are gigantic because compared to conventional vesicles, they're indeed large, but you still need a microscope to see them. The advantage is that they display the response of the membrane at a cell size scale, and they also represent an excellent biomimetic compartment. You can start reconstituting proteins in them, reconstituting a cytoskeleton, and this is how you can try to build an artificial minimal cell. We prepare them starting bottom up from lipids, but you can also force the cell to make you a giant vesicle. They're also called blebs, or giant plasma membrane vesicles. And you do that by exposing the cells to a cocktail of chemicals. Then they produce these blebs, you can harvest them. And you're going to be surprised that the mechanical properties of these blebs are very close to those measured on model giant vesicles made out of lipids, suggesting that the lipid bilayer is the one defining the mechanics and the major properties of the plasma membrane. We use giant vesicles to measure properties of membranes, and we develop techniques based on this. And this is a summary slide with them. If you take a lipid bilayer and you stretch it, you're going to the response is going to be characterized by the stretching elasticity modulus, which you can measure by aspirating giant vesicles in a glass capillary, applying some suction pressure, and measuring the area change as a function of tension. What you're going to find out is that the stretching elasticity modulus is around 200 millinewton per meter, which is the modulus of a rubber sheet of the same thickness as that of the membrane that you're going to measure. Bending is characterized by the bending rigidity, which has units of energy, kBt. It's around 20 kBt, which means that if several water molecules hit the membrane simultaneously, it would flex. And this is what you see directly under the microscope. The vesicles fluctuate if they are deflated. By detecting their contour, you do fluctuation spectroscopy to measure the bending rigidity. If you displace the lipids relative to each other, the resistance is characterized by the shear surface viscosity, which you can measure by taking a bead with an optical tweezer, sticking the bead to the membrane and shearing then the membrane with it, either by letting it to fall down as a micro version of the Stokes viscosimeter or letting it diffuse. The shear viscosity that you measure is the shear surface viscosity. It's around this number. If you want to convert it to bulk viscosity to get a feeling about this, you are going to get viscosity which is around 1,000 times higher than the viscosity of water. It's still relatively easy to move lipids and proteins in the membrane because the dissipation occurs into the environment. The membrane is so thin. If you have this tool with optical tweezer and a bead stuck to the membrane, you can pull tubes and do curvature assays at this highly curved segment of the membrane. And if you stretch the membrane way too much, it would rupture at the lysest tension of around 10 millinewtons per meter. And what we do in our lab is that we create pores in a very defined way using electric fields. And if you measure the dynamics of pore closure, which is extremely fast, we use a super high speed digital camera to monitor, you can measure the edge tension. If you got interested in all this, I can recommend that you have a look at this giant book. It's a giant book with 600 and more pages, a giant book about giant vesicles, where different protocols for their preparation and different methods for measuring various things on membranes are summarized. In all of these cases that I was describing until now, we most of the time try to find and work with an ideal vesicles, no inclusions, no defects inside. And then very often in certain samples, you see that the predominant fraction of the vesicles have tubes. Tubes can be inside, outside, they can be thin and cylindrical, they can be necklace-like, protein-like, and they mean something. They mean non-zero spontaneous curvature in the membrane. The membrane spontaneous curvature describes the bilayer asymmetry. It is caused by different molecular mechanisms, asymmetry in the leaflets, asymmetry in the buffer, absorbing ions or proteins which do that asymmetrically. The nomenclature is such that if the membrane curves outward, it's positive. If it curves inward, it's a negative spontaneous curvature. And it's evidenced by processes such as budding. Here, this is an example of small spontaneous curvature, where the bud is relatively large, and this is high negative curvature because the tubes are inward and very tiny. I'm going to tell you a few stories about tubes. The first one is about GM1, this sugar lipid, which is predominantly situated on the outer leaflet of biological membrane. So it's asymmetrically distributed. When we prepared vesicles doped with small fractions of GM1, and this was work done by Nico Fricke and Tripta Bhatia, we see that the majority of the vesicles have tubes, which suggests that it's a negative spontaneous curvature. We speculated that GM1 is asymmetrically distributed with more GM1 on the inside. These tubes are connected to the vesicle body, and we know about that by aspirating these vesicles with a micropipette, which absorbs the tubes back to the vesicle surface. If you release then the tension, all the tubes reform. And the surprising thing is that around 25 to 50% of the vesicle area can distort in tubes. And this might be a way how cells regulate their area, storing area in such tubular structures. So why tubes form? The reason is that GM1 can desorb from the membrane because it's also slightly water soluble. If we prepare the vesicles and we observe them directly in the chamber we prepare them, there are no tubes. The GM1 is symmetrically distributed on the membrane, inside, outside. If we dilute them, what we do is that we remove some of the GM1 outside in the bulk, then it starts desorbing from the membrane. It creates this asymmetry that you have on the inner leaflet, more GM1, and then we observe inward tubes because of this negative spontaneous curvature. If we do the opposite, we add now more GM1 outside, we increase the concentration of GM1 on the outer leaflet, which stabilizes positive spontaneous curvature, and we have outward tubes. We quantify this, and this is work done by Raktim Dasgupta. We quantify this by aspirating the vesicles. With a micropipette, we can measure the aspiration tension on the tension of the membrane. And with the optical tweezer, we pull a tube with which we can measure also the force. And the force is proportional to this term, including the tension. And you have an additional term reflecting the spontaneous curvature of the membrane. You can think about this as a tension contribution. If you pull inward tubes, and we manage to do that as well, the sign here changes because of the direction of the force. Now, here's some data. We have the force plotted as a function of the square root of the tension. The slope would give you the bending rigidity. The intercept would give you the spontaneous curvature. If we look at the black data, this is just pure POPC, symmetric membrane. The intercept is 0, and this is indeed the case. So the spontaneous curvature is 0. If we add GM1 asymmetrically, we see that this intercept changes, increases. If we pull inward tubes, this intercept is negative because of the change in the sign. So from both of these measurements on the same vesicles, we get values for the spontaneous curvature, which is of the order of 1/200 nanometers, 1/100 nanometers, which is substantial and comparable to curvatures generated by proteins. And then we wonder, well, how about ions? If we have buffer asymmetry across the membrane, can this generate large curvature? And this question is motivated by the solution asymmetry across the plasma membrane. Outside, you have a lot of sodium and chloride ions. Inside, you have potassium ions, a lot, but no chlorine ions. And we created a simple system at low A high asymmetry mimicking this. And the symmetric, almost symmetric system was taking giant vesicles with just a little bit of sugar inside and a little bit of salt, and compare it to a system where you have a lot of sugar inside and isotonic concentrations of sodium chloride outside at concentration which are physiological, 150 millimolar. Then Marzi Karimi did the same exercise, measuring the force as a function of square root of the tension and looking at the intercept. For the membranes at low asymmetry, The intercept was negligible, so this was suggested negligible spontaneous curvature, but for membranes with high asymmetry, the intercept was substantial, corresponding to negative spontaneous curvature, which means that the membrane wants to bend away from the salt. And this spontaneous curvature is of the order of 1/120 nanometers, which also should tell you that the tubes that you observe in the system have a mean diameter, which is about 100 nanometers. We can now also directly measure tube diameters, and this work was done by Debjit Roy, Jan Steinkühler, watch out for safety in your lab when you work with lasers, and Ziliang Cao. And we use super resolution or STED, stimulated emission depletion microscopy, with which we imaged vesicles aspirated in a pipette. We pull tubes and we look at cross sections of these tubes. With confocal microscopy, you don't see much. With STED, if the tube is in focus, you should get two peaks, and this is what we see. From the distance between the peaks, we can measure the tube diameter. Now, if you plot this tube diameter measured with STED versus theoretically predicted using a curvature elasticity model, which says that the tube diameter is proportional to the square root of the bending rigidity scaled by the mechanical tension, you see that all the data lies on a line with slope 1 and intercept 0. So this confirms the curvature elasticity model. And it also tells us that if you are able to pull tubes or even measure just tubes in cells, you can actually, by measuring their diameter, and knowing approximately the bending rigidity of these membranes, you can actually, in this way, assess the membrane tension. So I told you about GM1 and asymmetry. I'm going to tell you something about PEG, or crowding agent. Why crowding? Now, if we zoom into the cytoplasm, this is not a conventional solution. This is a highly concentrated solution with macromolecules. And this high concentrations of polymers should tell you also that according to a Gibbs phase rule, you should have phase separation. And this crowding has been already demonstrated to lead to local phase separation and the formation of membraneless organelles, which represent condensates or protein-rich droplets. So the way we do crowding in giant vesicles, and this is work by Yanhong Li and Yonggang Liu, is to load the vesicles with macromolecules such as PEG and dextran. Here, the membrane is in red. It sits on a substrate. This is a vertical cross-section, and a small fraction of dextran is labeled in green. We first did the homework to measure the binodal of the PEG dextran solutions. At low concentrations, you have homogeneous aqueous solution. If you cross the binodal, you have aqueous phase separation, then create two phases, PEG-rich one, which is lighter, and the dextran-rich phase, which is heavier. If you cross this binodal in a vesicle by simply deflating it and increasing the concentrations of the polymers, this is what you observe. You see the formation of the heavy dextran-rich droplet at the bottom of the vesicle. It does not want to wet the membrane, but then at certain concentrations, it can start wetting the soft membrane. If you deflate even further, some of the excess area, we observe that it goes at the interface between the two aqueous phases, the dextran-rich one and the PEG-rich one. And this is understandable because this accumulation of membrane lowers the interfacial tension between the two aqueous phases. But what we were surprised to find is that this membrane does not fold into a bilayer, but if you just look on top of it, you're going to see that it's a spaghetti-like structure of nanotubes. These nanotubes mean negative spontaneous curvature, and we confirm that this origin of spontaneous curvature is the weak asymmetric adsorption of PEG, which happens only on the inner leaflet of the membrane. PEG outside is removed, and this was confirmed also with simulations by Grafmüller. The last story that I want to tell you about is about more complex membranes, or blebs, and this is work done by Jan Steinkühler, which just came out in Advanced Science. So what Jan did is to create blebs, or giant plasma membrane vesicles, by exposing the cells to N-ethylmalamide, which is a conventional chemical to induce blebbing. And after harvesting these blebs, he sees that they're extremely tubulated. These are tubulated giant plasma membrane vesicles. We call them TGPMVs. The surprising thing was that if you compare their elasticity, if you measure their elasticity by applying tension and measuring the relative area change, you're going to see that they very much reflect the behavior of cells, which at small tensions have a large area extension. This is how also TGPMVs behave. They have a superelastic response. They reproduce the superelastic response of cells. GPMVs or blebs that you create without tubes, which you can do by using paraformaldehyde, behave just like conventional lipid membranes. So we were wondering where this superelastic response comes from. We first suspected maybe it is the asymmetry in the tubes, but if you have homogeneous asymmetric vesicles with homogeneous membrane composition and you aspirate them, there is a critical tension at which just the tube starts reabsorbing and the vesicle starts flowing in inside the aspiration pipe. And this is not the case with TGPMVs, which is why we speculated that it's also that apart from being asymmetric, the membrane is probably non-homogeneous. So it's heterogeneous. And the way we confirm this is by using FLIM, fluorescence lifetime image microscopy. These images, practically the color of this and the pixels of these images reflects the lifetime of the dye. It's the same dye that is distributed between the tubes and the outer membrane. And we see that this the lifetime of this dye, this is the spectrum of it. This is the membrane, the dye in the outer membrane, the dye in the nanotubes have a longer lifetime. But when you aspirate these vesicles, we see that the composition in the outer membrane shifts. So this is the delta, which is reflected in the lifetime. And this is how we concluded that the membrane is heterogeneous. And this aspiration, by changing the tension, you are practically changing the membrane composition. And this is the origin of the superelastic behavior that we observe, the combination of curvature and membrane heterogeneity. So one final thing I wanted to mention very briefly is that if you have control over the spontaneous curvature, you can even drive division. To start with, you know that the vesicle morphology is controlled by the volume to area ratio and the spontaneous curvature. If you start with a spherical vesicle somewhere here and you start deflating it, you can cross the budding binodal, so the vesicle would bud. If you quench it even deeper, you're going to end up with a dumbbell vesicle with a little neck. And now, if you start increasing the spontaneous curvature at this point, you can get fission of this neck or division, constriction of this neck here, or division of the vesicle, simply because the spontaneous curvature can induce a constriction force, which is substantial, up to 100 piconewton. Here, this is the neck curvature. And the way we modulated the spontaneous curvature in this case was using anti-A lipids that can bind histag molecules. This was histag GFP. The example here that I'm going to show is of a vesicle which has a lot of inclusions, which makes it easier to see. That is already in this dumbbell shape. It's trapped into a microfluidic device. And about now, we introduce the GFP histag, which binds to the membrane, induces a spontaneous curvature, and the neck between the two buds is fissioned, and one of the vesicles goes away. To summarize, instead of conclusion, membranes don't need much. A little asymmetry or droplet wetting is enough to trigger tube sprouting, engulfment, budding, or even fission, as I just demonstrated. Isn't it then obvious that the shaping of organelles, such as the smooth endoplasmic reticuloid, Golgi, or mitochondria, can be driven by simple physicochemical processes such as spontaneous curvature generation, wetting, or phase separation? And with this, I'll conclude, and I'll thank Professor Lipovsky, the host in our department, with whom I have extensive discussions of the theoretical background of these projects, and of course, my group, which is here in a COVID-like environment. And I thank you for your attention. I would be more than happy to answer your questions.